Recording. Episode 7, take 1. Welcome to Quantum Kinetics Corporation First Diffusion Podcast Episode 7. I'm here with
Jason McCoy.
Jason McCoy. Welcome to have you back. How you been?
I've been good. I understand you've been working hard playing Twinkle Twinkle and getting down the song.
Yeah, I can actually play Twinkle Twinkle on a normal piano without any numbered notes on it.
Wow.
Just from heart.
Yeah.
Just from memory.
Once you get it, it kind of works. It's the sound. It's knowing where to press and knowing what sound to expect. But last time I was here, I said I was going to play something for you, and I actually brought you a different kind of an instrument. Now, if you meet a pretty girl and she asks you if you're a musician, you can say yes, and you can play her this.
Now, is that a tuning fork?
It's a 432 tuning fork, which is a big hit. And but listen to this. I have a question about it actually, because I bought this one and I bought this one, and I thought that I was going to be able to hit one of them, and that the other one would play. So let me just let me.
Because we talked about on episode 4 that if you hit one tuning fork that's matched, it'll make the other one ring too without touching.
Right, but that's not happening with this one, and I was curious why. So let me play it for you.
Yeah, it's aiming right at my mic.
Can you hear it?
Oh yeah.
Mic? That's away.
Yeah, that's
it comes
awesome.
through.
Oh, totally. That rings for a long time.
Yeah.
That's very much like our circuits at Quantum Kinetics. When you ring it with a unipolar pulse, boom, the electrode keeps ringing for a certain amount of time in the water.
Oh, interesting. Well, one of the things I wanted to ask you about was that, so I was expecting that because these are both 432 tuning forks, I could hit one. I probably shouldn't do that on the actual
Oh, that's
mic,
okay.
But
yeah.
And I was expecting it to make this one vibrate, but it doesn't.
You know
I was
why?
wondering, I was like, did I not get the right thing or what? Yeah, why is that?
No, you nailed it. So if you can I borrow that one for a second? So when you look at the box, the resonant cavity, you can see that there's a depth and a height, and it's made of a certain material, which is wood. Now this could be metal too. This is called a resonant cavity.
Okay.
And it's also known as a Helmholtz resonant cavity. And it's very similar to our circuits here at Quantum Kinetics, where we have a tuning, like literally a tuned cylinder that we pulse. We pulse it and it rings. And so you have this extra energy. Like you don't have to continually, you can.
Yeah.
But the reason why when you pick up that fork and you ring yours and this one doesn't start ringing, because go ahead and pick it up. We're going to do an experiment.
Here, you want the mallet thing?
Oh, sure. So you hold yours and I'll hold mine. So if I do this, notice how Jason is holding his tuning fork with his hand. This is literally like the ground of Earth. This is his resonant cavity chamber is different than this one piece of wood. And because you haven't matched the chambers properly, your tuning fork will never ring as like this one, even though they're the same tune. Because if you have to have this box exactly the same as attached to that box. It's exactly the same as radio. Now, Jason, we're like the Sesame Street of cold nuclear fusion, so I have to bring in...
Gotta show it.
So this is a really old RCA, like this is actually an RCA radio, which has the tuning knob where you can tune the radio frequency that you want, and that is affixed to a variable capacitor, which is right here, right there. And if you can look real closely, you can see this rod. This is an inductor with a ferrite core in it.
What does that even mean?
That essentially is the same. What you're looking at here inside this RCA radio is the same thing as that box.
It resonates with vibration waves that are in the, like, radio waves that are in the air, making that thing resonate?
Yeah, so this is the antenna that's affixed to the circuit, and when the waves of like 106.1 hit this, like the tuning fork, it goes inside the box, which is the inductor and the capacitor.
Okay.
So that box is the resonant cavity.
And the tuning fork thing on top is like the antenna.
Totally.
So the antenna vibrates with the radio wave that resonates the chamber, and then what happens after that? Does that get amplified, and is that what we hear?
Right, and that's what goes into the circuit of your speaker with the little transformer, and the impedance is matched, and then it sends a voltage, either 12 volts or 9 volts, depending, to a little speaker that has 8 ohms of resistance, which has the same impedance, and then you hear in the car. You can hear people talking. You can hear people singing, you can hear music, and all this awesome love is being projected into your ears, and you're jamming out while you're driving, in the summer. Yeah. And so that's
singing
exactly
along off key a little bit, but that's okay.
Well, no one's in the car with you, right?
Yeah. With the road noise, it's actually takes the edge off of the pitchiness, but yeah, that's good.
Oh, that's perfect. And that's exactly what happens with the arc reactor. The arc reactor, and by the way, like Jason mentioned that I should tell everyone, is this one right here that we show is a toy. This is a 5-volt toy that just plugs into a computer. The real one that actually does thermonuclear fusion from 11.6 million all the way up to 200 million degrees and more is right here in the back, right over Iron Man's head.
This thing right here, yeah?
Yeah, that's the real one. That's the real radio, because it has the coils wrapped around it, and then those attach to the capacitance of the rings, and they're tuned to resonate with the ambient air and the ambientness of free space. And so then the circuit amplifies everything around it, and then it starts oscillating, particle oscillation as an energy generator to induce safe, cold neutrons. And I don't know if you want to talk about what the difference between a fast neutron or a cold neutron is.
Well, I want to ask about it. I think you might be the one talking about it. But yeah, I was wondering about that. Okay, so you, on previous podcasts, you've mentioned safe, clean nuclear fusion with cold electrons.
Yes.
I mean cold neutrons. Cold neutrons.
Both.
Okay.
Both.
So what's a cold neutron? What's a fast neutron? Why are we even talking about neutrons? Why do neutrons have a relevance in this?
So if you're doing a nuclear reaction, by definition, you have to have a nuclear flux, which means electrons either falling into the nucleus, turning the nucleus into something different. The neutron turns into a proton, or proton turns into a neutron. That would be a nuclear reaction because it's in dealing with the nucleus of the atom. So anytime the nucleus of the atom is changing or being pulled or moved or whatever, that would be a nuclear event. And so a fast neutron is like if I had a rubber band, and I pulled it back so far, and then I released it, and then it hit my hand, it would really hurt.
I've done that before. I actually did that on a baby once. They had one of those little party hat things,
yes.
And we were trying to adjust the strap, and it snapped. And that was a bad birthday. The birthday boy was not happy that day.
Was that
it was him. Yeah,
okay.
It was my bad too. I was like, I'm going to adjust the thing, and I let go of it, and it snapped right back, and it was just like changed the whole vibe of the thing. But
so that phenomenon where the baby cries after you adjust the hat is exactly what the hot fusion guys are doing every single time they turn on their reactors. They're doing fast neutrons.
They're making babies cry.
Well,
so to speak,
in a metaphoric way, they are definitely making babies cry because fast neutrons kill everything. It kills biology. It kills metals. It embrittles the metal of the reactor, and that's why hot fusion is not a viable option, hasn't been for 80 years, and they need to stop doing that.
All right, let me ask you a question about that. Yeah. Okay, you say that it's not a viable option, but I'm sure there's a bunch of people out in the population who have some knowledge of different kinds of reactors. And they might say, well, they'll just build a better shield. They'll eventually figure out how to make a graphite containment system or whatever in the thorium reactors like you talked about last time.
Well, so thorium is a fission type of reactor. It's different than a hot fusion, like a tokamak or a stellarator and inertial confinement or something like that. So hot fusion does fusion of hydrogen or
Okay.
helium or like
Okay.
deuterium or tritium.
Not fission, which divides it.
Right. Fission is
Yeah.
where you divide the heavy element down,
Yeah.
then it releases fast neutrons.
Okay, so fusion creates these hot, dangerous,
Mm-hmm.
fast-moving neutrons
Right.
that basically blast and harm the containment system that they're in, therefore making it a difficult way of creating sustainable nuclear energy. Is that right?
That is exactly
Okay.
100% right. And it's like if you were to take that string from the party hat and just keep smacking the baby's chin with it over and over and
Right.
over, I mean, the baby's going to be pretty upset with you and start
Yeah.
crying, and it's going to be a bad birthday. And that's what we have going on right now in the industry of hot fusion. We have investors putting hundreds of millions and sometimes even billions of dollars into these hot fusion reactors that are being bombarded by fast neutrons. And some of these neutrons, Jason, go all the way up to the 14.2 million electron volt neutron, which is basically one of the most dangerous things in the universe. And I'm just going to tell you guys, it's not the way to go. You need to slow down. You need to stop and think about, hey, is there a smarter way to do this? Is there a better way to do this? Because it hasn't worked in 80 years. It's not going to work in another 80 years. And even if you do get it to function for a certain amount of time, you're going to have a plethora of problems in terms of your reactors breaking down. You're going to have issues with radiation from transmutation of like the borated concrete walls. It's just going to be a really bad situation because you're going to have to go bury that concrete into the ground, and then it's going to poison the ground. So here at Quantum Kinetics, what we've done is we've discovered and patented and trademarked a totally new type of neutron flux, which is cold neutrons. And what that means is we don't pull the rubber band back very far. We just pull it back like half a volt, not 14 million volts, but just half a volt, and then we let go. But we've done it in such a way that it's like you're clapping your hands, or like we were talking about the cymatic frequencies when we were at lunch, where you create these wells, the quantum kinetic well, and it holds the neutron flux in a safe way.
Yeah. So I noticed that like in those patterns, I look at the stuff so visually.
I'm excited.
When they show overlapping wave patterns,
Mhm.
there's these like, I'm making my hands like that because there's this sort of like beautiful pattern where the waves are overlapping in some spots.
Additive.
Okay. And then in other spots, there's nothing.
Subtractive.
Okay. And then when you see a cymatic, when they put sand on top of a plate and then play sound through it,
Mhm.
you see the sand settle in certain spots, and it makes these incredible patterns.
And they're beautiful.
And what's happening where the sand settles? What is that?
So where the sand settles, it depends on your perspective of what you're looking at, but it could be a condensation. That could be the well. Although you look at it and it looks like it's up and high, technically you're condensing the
Right.
material into this spot. So technically that's a well.
So there's too much. Okay, so there's too much vibration energy on the spot on some spots that clears them out.
That would,
And they
yes,
sort of push it into these troughs.
correct.
And that's the quantum kinetic well by analogy of the wave function stuff.
Correct. And that's why we can do nuclear fusion safely, and we can actually create new elements. We can actually create carbon, we can create nitrogen, we can create aluminum, we can do iron, we can turn the voltage up and go all the way to uranium if we want. And our studies have showed that we have actually manipulated plutonium to some degrees in some of our reactors. So what we're saying, essentially taken from the top, is that the resonant frequency cavity of the tuning fork is analogous to the radio, which then makes nuclear fusion possible at a safe way for industry. And it's easy, it's safe, it's pretty, and it creates things that we never thought were possible. And I'm just going to give you guys a little bit of a teaser since you're been here for 14, 15 minutes, still staying tuned.
Inside scoop, huh?
Inside scoop, ready? Breaking news.
Yeah.
So we just finished a research study with an institution, which I can't say because we're on NDA, but when we got the data back, the lab specialist said, I don't know how you're doing that, but you're doing photosynthesis without sunlight. And Randall, he says, on the contrary, there is a sun. It's a star in a jar. There's a star inside the reactor.
Wow.
And so what we're telling you, ladies and gentlemen, is that quantum kinetics has figured out a really beautiful, safe way to do nuclear fusion, not just for energy generation, but also many other industries that we haven't even thought of yet. And this could go all the way to what you may want to talk about today is, what does the future look like?
Yeah, I mean, I have talked to you several times. My background being in computer animation and graphics, and just being like a visual kind of person, I'm always looking at like, let's just like apply this technology to cool future tech.
Yeah.
And you actually told me like, hey, you got to like hold up on the heavy stuff first. So to begin with, something like, is it possible to power a car? Is it possible to power a motorcycle?
Yes.
Or a boat, or a steam engine, or a oil tanker, or like our traditional methods of transportation? Is it possible to power it with the arc reactor in some way?
Yeah. In every type of new revolutionary technology, Jason, you have to take baby steps. And actually, this is one of the things that the scientist that we were working with recently, she wrote me an email and said, I know this is really heavy duty stuff, and, it's really hard to, do this, but you just have to understand you got to take baby steps. And she's totally right.
Inventors are not good at baby steps. Why would we want to take a baby step when you can, kick down the door and barge in? That's the fun of it. I know this is like,
you're preaching to the choir again.
I know. And I want to talk about being an inventor too, because I think that's, you and I have had so many conversations about that.
Yeah.
And about how beautiful it is as a life. It's nobody gets to do what you're doing in your day. On the other hand, it's a very strange lifestyle. It's very demanding. There's these stretches where nobody truly even understands what you're working on.
Mm-hmm.
And then you come up and you find this thing that's so incredible. You want to share it with the world. And then you got to make a business out of it. And then you got to be a businessman and part-time lawyer, by the way. Like, it's
and marketing guy and editor.
And podcast bro or whatever, all of these different things. So that's something I wanted to ask you about, on like a personal message. You're always on here talking about the technology, and that's awesome. But McKane, the guy, and the inventor, we had there was a investors meeting the other night.
Mm-hmm.
And
thank you all for coming.
Yeah, no, it was fun. I was glad I made it to that too. And somebody asked you a really interesting question. Probably one that not everybody thought was interesting, but I sure did.
Yeah.
Which is, what is your daily routine? Right? So, in light of the like massive spectrum of things you're working on, what is your daily routine, and how do you prioritize what to do next?
It's like being a captain on a ship that is like getting ready to set sea. Like you gotta clean the deck, you gotta oil, the holes, you gotta like patch the sails and sew the sails, and you gotta do the ropes, and you gotta make the ropes, and then you gotta like set everything aside and say, this is what this is, and then you gotta label everything. It's like every single day, Jason, is a different job. And it could be emails, it could be writing a patent. It could be, going in the lab and doing an experiment with a national entity or whatever. Yeah. So, or even talking to investors and calming them down because they don't understand quite where the direction's going. And so it's just an ongoing evolutionary thing being a CEO. Yeah. And, I look up to Steve Jobs a lot, because Steve Jobs with Macintosh, he said basically the same thing. It's like, you just have to trust yourself. You have to trust your gut, and you have to be like, look, there are bozos out there that are going the wrong direction. Screw them. Just keep doing what you really love in your heart, and just really do the best you can.
Well, the thing I was really going for, and I know, ironically, creating the business is I always joke that creating the world-changing idea was the easy part. It's creating the business that takes the genius. Yeah. For some reason, the business is so challenging, and I've gone through so many partners as you have, and different things. But what I really wanted to ask you about being an inventor is the thrill.
Yeah.
That moment, that day that you come in here at like, you're rolling out of bed, you got the cereal, but you got something you want to work on.
Yeah.
You got that thing that you've been dying to test. What is that day like? How fun is that?
Well, and I'm preaching in the choir because
Yeah.
you know this feeling too, and you just want to like get it out of me. And
let's talk about the good stuff.
yeah, it's so like when you're about to turn on that thing for the first time, and you know something's going to happen, or you have a feeling it's going to happen.
Right.
It's going to be this time. You come in with like, you start almost sweating. Like you're so nervous and you're so like excited, and you're like, you start getting jittery almost, excited, jittery, and so it's just the most amazing thing when you do it and it turns on for the first time. It's a lot like what Edison said when he first saw the light bulb come on, way back in the day. He's like, all the people that were in the room when they saw that light bulb come on, and it was staying on for like 5 minutes, and then 10 minutes, and then 15 minutes. Because before, it would only turn on for like 30 seconds and pop.
Because it burned out the filament. Right?
Correct.
Yeah.
And so they did hundreds and thousands of different iterations, and then this one time when it stayed on for a minute, and then 2 minutes.
And what was that, tungsten? What is
it? It was a carbon, actually.
A carbon, because it could handle the heat?
Yeah, so the thing about carbon is funny, because carbon is conductive, but it's really rigidly strong because of its lattice, but it still can conduct. And it's also a resistor too. So that's why it can glow, because it's absorbing the electron flow, causing this emission to grow out, and this light to grow out, kind of like a star. And this is my theory too, that a star is not this gigantic big ball of gas. Mm-hmm. It's actually a gigantic sphere of carbon black magnetite rock that is so electrically agitated that it starts glowing like a incandescent bulb. That's my theory.
Instead of a bunch of hydrogen stuck in the middle of the core that's fusing with other hydrogen, making heavier elements. That kind of thing.
Yeah, because if you look at the sun, like you look up at our sun, it's yellow. What's the color of an incandescent bulb?
Yellow.
And then if you look at a plasma fusion reactor, hot fusion, what color is it? It's purple and pink. Did you know in astronomy that there's no such thing as a purple star or a pink star? It does not exist. There's no star that's pink.
Because it can't radiate that kind of light or something?
Well, it's color theory and astronomy, and it has to do with the ultraviolet catastrophe and chroma key and all this stuff. But like, essentially what it means is that it's kind of similar to when a meteorite goes through the atmosphere. If it's iron-based, it's going to be orange.
Is this spectronomy that you're talking about?
Spectroscopy.
Spectroscopy.
Yeah.
Okay.
Yeah, it's
that's a spell.
Astronomy.
Put that one up on the have the Iron Man guy spell that out when you. By the way, I love the edits with the Iron Man guy. I'm always like, half of the reason I watch the podcast, I'm like, what's going to happen in between?
Well, it's funny. It's so hard to like I like it too.
Yeah.
But some people have emailed me like, I don't really like that. It's kind of cheesy and corny. And I'm like,
fun.
It's
a fun accent.
I have fun with it, and I know you like it because we're kids. Like, and this is another thing about the technology too, is like, if you're a kid deep down inside and you have the love for discovery.
Yeah.
Like I think you were telling me a story when you were talking to your dad. When you were a kid, you'd always ask him a million questions.
Oh man, I'd grill that guy.
Yeah, tell me about your dad and asking questions, being inquisitive.
So he was an engineer type person, like Brighton.
Yeah.
Right? That guy is an engineer.
Brighton's a stud, dude.
He, like, the first minute I saw that guy, I'm like, oh, he's the guy who's going to be building stuff? Great. That's the natural guy, like, put on the planet, born to do that kind of person. Some people are natural engineers. Some people are more artistic. Some people are some kind of hybrid mix.
Yeah.
And he loved science. He loved geometry. He worked on a variety of sort of interesting ideas, and he was definitely interested in the sea. He was fascinated by the sea and all of those types
Did he
of things.
say anything specific about the ocean that made him interested in the ocean?
Ironically, well, there's growing algae was one.
Okay.
Mining the bottom of the seafloor. Evidently, there's like minerals on the bottom of the seafloor.
Yeah, they're called like nodules.
Yeah, I saw that. Yeah. Off Japan, is it somewhere in that area?
Actually, they're all over the place. They're finding them, and these little nodules are very strange because just recently they did a study where they had an O2 sensor go down to the bottom of the ocean, and they're like checking the oxygen level.
Yeah, the oxygen thing. Yeah.
Yeah, and then they went down with the sensor, and they found as they got closer to the bottom of the ocean, there was a lot more oxygen. They're like, wait, how is that possible? And they chalked it up to their instruments were failing out, and there was something wrong with the pressure. So they came back like 2 years later in the same spot and did with upgraded sensors, and they did it again, and they got the same numbers. And so they're like, wait, what are these? How that's an anomaly.
Yeah.
How is there more oxygen at the bottom of the ocean than there is at the top? And there's an interesting thing that happens in the early formation of Earth is that there's a crazy period during early formation of Earth where there's the great oxygenation period.
I thought that was because algae, or was it algae or bacteria came on the scene and it started pumping out?
I want to say,
it's got to
don't quote me on this, but I think it was cyanobacteria or something like that. Don't quote me on that. We may have to look that up. But when this cyanobacteria grew exponentially on the planet, it oxygenated the planet like crazy, which then caused the atmosphere to grow around because of the gravity was pulling in the oxygen. And then that's what caused Earth to be able to, we could live on it.
We have a thin film of gas around the ball of the planet.
I think they call it a biosphere, actually.
Right, yeah, or atmosphere, right?
Yeah. It's
okay.
And so your dad kind of had an intuition about the ocean, right?
Yeah, he was fascinated by it. I don't like the ocean. I wouldn't swim in the ocean. There's too many sharks and weird stuff in there. But I remember him coming out of the ocean one time. One of my fondest memories was we went to this beach, and my mom was like, just look out over the water. And I was like, okay, we're sitting there waiting 5 minutes and so on. And then all of a sudden, my dad comes out of the water, walks out of the water in a wetsuit and a scuba outfit, and was telling me about it. He said it was so interesting because it was 3-dimensional, and the whole world is around you. But the ocean is an incredible place, and the way that those nodules that you were talking about on the bottom of the ocean, so are they creating oxygen? Or what? And I thought they were made out of metal, some kind of metal.
So the scientists, and if I can, again, don't quote me on this, but I just saw it on YouTube not too long ago.
I can already see your message thing, ding, 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 like all the
I'm trying not to mess up. But from my understanding is these nodules are actually mesomorphic materials that are basically metal that have their own electrolysis event happening inside them. That's what the scientists are saying.
Electrolysis event.
So electrolysis.
Splitting oxygen, or splitting water into hydrogen and oxygen?
Correct. Okay. They say that and this is what they say, the scientists will say that they don't actually know the true mechanism.
Okay.
So they just think that it's a electrochemical reaction that causes electrolysis, which is splitting oxygen and hydrogen apart from the ocean. And so because of the it actually is a dense gravity down there, and a pressure, that the oxygen, because it's heavier, is getting stuck on the bottom of the ocean. And then the hydrogen's going up and then like turning and dissolving and causing a pH change and all that stuff. But
that kind of makes sense. So the oxygen's not like bubbling up because it's heavier. It just
so it just kind of stays on the ground level.
That's why there's such a high level of oxygen down there.
Correct, and it's off-gassing all the time too. So again, the point is the ocean and science is we're always learning something new. Every single year, we're learning something new about the universe and ourselves.
Yeah.
And with nuclear fusion, we too are doing the same things. And so I just want to preface to everyone watching is that don't assume you know everything, because you definitely don't, right? You just we figured out cold nuclear fusion, got a patent and trademarked, and we're now showing the world and trying to teach you guys. But that doesn't mean that we're experts. Matter of fact, we're just the beginning frontier.
There's more to learn.
Yeah, so you need to be humble and have your hand open.
When you tell people, okay, I have a couple of questions. I remember watching this show on the guy who invented the snowboard. And I think
was it Burton?
I think it was, yeah. The guy would say when he went on a plane and somebody would ask him what he did, he would be like at first he would actually tell them like, I invented this thing. It's like a surfboard, but it's for the snow. And they would like, it was a half an hour conversation for sure. And him just trying to like reiterate, they're not skis. They're one thing like a, so when you're on a plane or you meet somebody for the first time and they ask you, so what do you do? How do you go, by the way, have you ever given that like the actual answer and watched people like glaze over as they're like 20 minutes later and you're like, and the nuclear fusion and the atoms and da-da-da, and they're like,
it depends if it's a really cute girl or
yeah.
it depends.
Surprisingly enough, they're not so interested in the science, the depth of the science, as much as you might want to be explaining it. I've made that mistake a time or two. 20 minutes
so
later.
What do you do, Jason? I invented numbered notes.
Yeah.
Tell me about that.
Music theory by number, not as cool as lead guitarist in a primary band. I thought you'd get a lot of groupies with music theory, but I was wrong. I was off by an instrument.
By a factor of 10.
Yeah, not so interested. But what about you? How do you say you're a scientist? Do you say you're an inventor? Do you say you're running a business? Do you say you're pole vault champion? Do you where do you go with that?
Man, I mean, it depends on the person, but honestly, you kind of have to just gauge your audience. I mean, obviously, like you have to gauge your audience, but I just tell them that I locked myself in a garage and I invented something cool. And they're, oh, well, tell me about that. And so you just kind of have to fish people in and say, like, you don't give them, I patented the arc reactor. They'll go, you're crazy. That's impossible. Like, you just got to fish people in, and it's. I'll tell you what, this journey has really been exciting. Being an inventor is probably the most stressful thing I could have ever done in my entire life and probably will ever do. Although I have never had kids, so maybe that's stressful too. You probably have kids, so
it's different. It's not the same. The inventing is different.
Yeah.
It's a career choice and a lifestyle and a devotion and believing in yourself when you can't prove everything you're exploring while you're exploring it. That's the problem. Is that you might not have the answer yet, and what are you going to tell somebody?
I'm going to share a little story because you just brought that up.
Sure.
We just did a study with a lab, and like they said, you're doing this, and that's impossible. You're doing things exponential level that no one's ever seen before, and the star in the jar. Mm-hmm. And I'm going to be honest with the audience, like when we found out that data, I was messed up for a whole day. Because I knew that eventually I'm going to have to try to explain this to people in a coherent way that they're going to have to understand. It's like fishing up a giant whale. And when you make the discovery, something hits you and says, oh, I have to explain this now to the people that already don't believe me or believe my work or our work or whatever.
Right.
And it hit me so hard that I was kind of out of it for a whole day, and I just want everyone to know that don't assume you know everything about the universe, because you need to have an open mind and an open heart about what is possible with this technology. Because if you harden your heart and say that something's not possible, just like Henry Ford said, if you believe you can do it or you can't do it, you're right.
Yeah.
Right?
Yeah.
And so it's kind of amazing that even the scientists that have seen our data are also very excited about it. And it's like, keep going. And when people tell you to keep going, it really does feel good to have people do that.
They're rooting for you.
They're rooting for us. They're rooting for the world. They're rooting for the possibility of saving the world, which this technology can totally do. So here at Quantum Kinetics, I mean, like Jason coming on and Brighton and Randall and even our investors, which we really appreciate you guys coming on and making this all possible. We are not done yet, and there is so much more to learn about the universe and even ourselves. And I mean, and learning about the radio, learning about nuclear fusion, learning about, when something doesn't work the first time, it doesn't mean it's not ever going to work. You just haven't met Mother Nature's criteria to make it work.
That thinking is something I've run into a lot teaching. I've taught for many, many years in so many different capacities. I've taught adults 3D animation.
Mm-hmm.
I've taught teenagers 3D animation. I've taught children how to code. I've taught adults how to code.
Mm-hmm.
And people, they have this thing where if they try something literally once, if it doesn't work, they're done. They're like, it can't work. It can't be done. I'm not good at it. I'm never going to draw. Somebody told me something mean when I was 7, so I'm not doing it anymore. And it's understandable. It really
Mm-hmm.
is. Like you, part of, you've taught for a while, and you see that it's a very delicate thing about people have a lot of their personality wrapped up in that like having somebody help them learn something, or learning something they don't know, or trying not to look like they not understand something.
Do you think that has to do with the ego of the human intellect and the internalization of like the world around you? Like, it didn't work the first time, never going to make myself look like a fool again.
There's something to that. There's also something to the fact that when we teach, this is on the teacher side of things.
Mm-hmm.
When you're not a professional teacher and somebody wants to learn something from you, people who haven't been taught the grace of understanding that somebody does not understand something yet, and they're asking you to learn, and it's a vulnerable thing, you have to treat that with immaculate conduct
and delicacy.
Yeah, because it's a very vulnerable thing to look at, to ask somebody like, hey, I don't understand how to like open this container, like how do I open it? And if somebody says, well, you should know how to do it, or can't you read the directions, or anything derogative, you're training that person to resist the idea of even asking how to learn something.
Mm-hmm.
So you have to be humble when you teach and when you learn, and you understand that there's this dance that's going to happen where at first you're not going to understand it, or you're going to apply preconceived notions.
I think that's really what it is that preconceived notion that this is the way things are supposed to be.
Yeah.
And this is what I was taught. And there's no other way around it. Like,
or it's already been tried before. I imagine you get that with cold nuclear fusion, right?
Wow.
A bunch of guys in the 90s tried it, McKane. Why are you even bothering, right? Nothing could have evolved since the 90s. I mean, how could you even dare to do the same thing? But as you probably know, right, there's other things that could have been tried, right? I mean...
Yeah, it's true. I mean, there is a major pariah around cold nuclear fusion. And I want to tell you, in the last 2 weeks, we've been surveying the YouTube's channels.
Interwebs
the interwebs. And we're starting to see that these scientists who have done cold nuclear fusion research are coming out and talking more openly about.
I saw that. That thing you sent me was the guy was like, "Hey, we're really doing it."
It was classified back in 1995 by Bill Clinton, and he saw the paperwork for it, and it was basically a hydrodynamical electromagnetic spheroid, blah blah blah. And what I'm trying to say essentially is that not just the academic community, not just the political influences, not just like the institutional societies of a collective consciousness have been pushing back on cold nuclear fusion. That's a lot of weight to be trying to go against, right? Like, for example, if you get good data results and you're at like an institution, the first thing that you get is mud thrown in your face, even though you're like, I did the experiment exactly like I'm supposed to. So what this movement represents, Jason, with quantum kinetics is that we are now awakening. This isn't not just about quantum kinetics. This is about all the academic institutions that have done cold nuclear fusion experiments that have gotten results that couldn't voice their opinion, you know? And this is a movement. And there are forces out there that have even told me, don't do these things. And I'm like, well, are you going to pay me? No. Okay, well, I'm moving on. I got to keep going because, you know, either you're with me or you're not with me. And so that's why we need everyone to understand that though this is not a traditional approach to a business, it is important to educate the people to a certain level so that they can accept the technology because they have enough knowledge.
So that along those lines of what is it that when somebody said to you, teach the world, the patent office, I think it was, right?
They mentioned in a phone call that well, they wrote in the acceptance allowance letter that basically prior art has failed to teach this method of electronics in any form or fashion. That's what the guy wrote. Can't say his name, but that's what he wrote. And then we got a phone call from the patent office saying that, you need to go teach the world and do it fast.
And so when they say teach the world, what is like one major thing that is, obviously we're doing these podcasts, we're educating people on different kinds of science, resonance, frequencies, atoms, electromagnetic spectrum, cymatics, periodic table,
bingo,
black holes,
you name it, we got it.
Island of instability. I want to ask you about that. I love that island of instability.
Okay, so we'll talk about the islands of instability, and then we'll talk about numbered notes, and then we'll close up.
Yeah.
So go ahead and ask the question about black holes. Or the island of stability, sorry.
Okay. Which
is the same thing.
Stability. Okay. I call it the island of instability.
Okay.
Not that I am right about that.
Well, tell me what the island of instability is first.
In my personal science. Well, so my understanding is that there's a section of the periodic table that has, I love this stuff because I'm like, what kind of freaky stuff is going on in that department, right?
Yeah,
because, okay, the way I understand the periodic table, right? This is great science guy stuff for you to tune up the understandings, as most people have. So the periodic table is the sequence of atoms,
music,
notes. By how many protons they have in the nucleus,
and neutrons.
Yep.
And each one can change. Like you can have more protons than neutrons, and you can have more neutrons than protons. And so.
And is that an isotope?
Yeah, it'd be an isotope of that.
Okay, it's the same amount of protons, but a different amount of neutrons. An isotope, right?
Yeah.
Okay.
And so this graph that you're talking about, we'll show it up on the screen, but it's kind of like a diagonal line that goes up into higher and higher elements.
Right.
And if you have a certain amount of protons, you could fall apart this way. If you have a certain amount of neutrons, you could fall apart that way.
Okay.
And so as you stay in the balance of like neutron to proton relationship, if you stay on that gradient line, it'll be stable.
Oh, okay. But
there's something beyond that.
Okay, but there's a section of the periodic table from whatever to whatever that numerically, like 114 to something or 113 to something, or
it depends if you're talking about the neutrons or the protons.
The protons. I'm just talking about the protons.
Yeah. Element. Which one are you talking? Element. What?
Well, I don't know exactly where the stability line ends.
Yeah. So there's a hypothetical after, like, when you get to like plutonium and all the other exotic ones that are super duper heavy, they start to basically, there's no way to hold them together. They just fall apart. It's kind of like a.
And why do they fall apart? That's what I'm getting at. Why do they fall apart?
There is some debate about why exactly they don't just keep going on this linear curve forever.
Is it the three-dimensional geometry of protons and neutrons?
I think it has to do with the electrons. The electrons cannot hold the shell together properly, and so either the electron falls in or the electrons shoot off, which then causes the nucleus to be even more unstable.
You know what else is interesting is that you talking about electrons falling into the nucleus.
Beta decay.
I've never even heard of that before. I thought the electrons just fly around in some kind of orbital shell, and they fall into the nucleus.
When you get into an electronic circuit like the cymatics that we talked about with the waves cresting and all that, you can create these wells, and that's where you get these concentrations of fluxes between neutron, proton, that kind of thing. When an electron falls out from the outer shell into the nucleus, typically what happens is the electron will fall into a proton, turning the proton into a neutron. Does that make sense?
Yeah, they sort of cancel each other out.
Well, it actually absorbs it. Like the proton will actually absorb into its belly an electron, thus changing the up quark, down quark, isospin, blah, 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 into a neutron. It's called quantum thermodynamics. That's actually what it's called.
Huh.
It's actually Richard Feynman stuff. And he had these really beautiful little pictures that he drew, and he got a Nobel Prize for it.
I've seen those. Those are like squiggly lines that
Bingo.
shoot out. Like,
exactly.
Okay. You just like beta decayed some energy because then you were able to merge with something else.
Yeah, and a neutron, when it turns into a proton, it just kicks off an electron. It shoots one off. So inside the belly of a nucleus is a bunch of electrons. and positrons, and virtual particles and virtual photons. But again, getting into the weeds and the lost in the sauce, just keep it simple. The island of stability, it's not instability, it's the island of stability, is a theoretical spot around element 115.
That's what it was, yeah.
Which is...
I've heard about that before.
There's a couple names for it. Moscovium, because it was actually synthesized in a particle accelerator in Moscow for like a nanosecond or a picosecond or something crazy, small amount of time. But then there's this guy from Area 51, Bob Lazar, who UFOs people know very well. He said that the element 115 is possible. And he said that way back in like the early 90s.
Possible to be stable.
To possibly be stable. Okay. And that he actually held it.
Huh.
Everyone thought he was a kook. And then 10 years later, we're synthesizing in our particle accelerators like it ain't no thing, right?
Huh.
And so,
Is
again,
that true? Right.
Yeah, and going back to what we talked about earlier is don't assume that you know everything.
Well, okay, so let's go on to that. Let's talk about stuff in science that people used to think was one way and then was another. I think I told you about this a while ago. There was a thing in astronomy where they thought that the Earth was the center of the
universe.
Yeah,
Galileo Galilei.
And they did the math, and the math panned out in such a way that it did track the planets incorrectly, as if the Earth was the center of the universe. And isn't that interesting? They could prove it mathematically. They could track the way that things were happening because they cooked up some mathematics that could do it, but it wasn't right.
And they only did it really for a two-body system, which is a core in the middle and then something going around it.
Right.
They didn't calculate the three-body problem, which is there is no mathematics for the three-body problem. I have a theory about that, and it has to do with numbered notes, the invention that you have with the 1 through 12.
Okay, what's that?
Is that just like the cymatics, when you hit the keys on the numbered notes, if you hit, say, like 3, 7, and 12, which when you hit those keys, they kind of wave on top of each other and create this really beautiful sound in your ears.
Right. It happens to be a minor chord, by the way. Just so you know what you did there. Yeah, it is. It's a minor chord.
Gee, imagine that.
Yeah.
Minor, major.
Yeah.
And so my theory is that the three-body problem is not solvable because there's something missing in the mathematics, which is some type of wave music notation to the gravitational three-body problem and also a multi-body problem. And so what I'm going to tell you, just to close up here, is that because of your invention, Jason, of numbered notes, which we talked about in episode 4, which you should totally check out, that I never knew music very well. I could barely play the piano. Hated music, actually. And now that I have discovered your technology with the numbered notes, I can play Twinkle, Twinkle, Little Star on the piano without even the numbers there. Because I'm just playing a phone number, and it's so much easier to remember the numbers.
Yeah.
And there's something that also happens in your brain, which is kind of like a black hole, because your brain absorbs information and holds it there, which is the information paradox of a black hole. If you can just cross the boundary between the electron absorbing the information and turning it into a proton, turning it into a neutron as data, if you can transfer that information effectively and efficiently using a gravitational well, which is numbers and resonances, you can amplify Mother Nature's forces and effects.
Is that what you mean when you say, like, love is fusion? By the way, I bet you have a
theory.
It's not so much a theory. I always wonder when you say that. I'm like, what does that mean exactly? But what I'm coming to understand a little bit more when you say love is fusion and you don't have to force it and all that kind of stuff is that there is a mechanism already existing in the universe to do the thing that you are accessing. That's what that means. You're not ramming stuff together in a particle accelerator or squeezing the plasma together through magnetic confinement. What you're doing is and this is like a crack at the technology, but vibrating the atoms in such a way where either they fuse together or they
Spallate.
Or they come apart.
Yeah, spallate.
Fusion or fission.
Correct. You can do both in this process, which we have found in our studies. You can do fusion and fission. And so...
And you can prove that, right?
Yes.
Through the tests.
Oh, yeah.
So when you go to a potential investor or you talk to another scientist and they say, hey, man, that's been done before. We tried cold fusion. What are your tests? What can you show you can do? Are those tests compelling enough to convince even a quote unquote professional scientist that this stuff is really happening?
Only if the scientist or person that's looking at the data, like our NPJ Nature magazine manuscript that we got published with clean water called Electrophysical Transmutation. Only if the scientists that come at it come with an open mind. I have had people reach out and say, hey, I don't think you're doing cold nuclear fusion. I don't see any research data to prove it. And I just lead them to the Electrophysical Transmutation EPT paper. And then they just disappear.
Okay,
they don't come back and say, this is dog poo-poo or whatever. They just disappear.
So let me ask you a quick question about that word you just said.
Physical
transmutation.
Yes.
So you're creating fusion by using electricity.
Good.
Not smashing it in a giant $1 billion facility.
Correct.
Why not just have a $1 billion facility?
Because it takes $1 billion to do it.
Why not just take $1 billion and just burn it and take the heat from burning all that money, power a steam generator? You probably could make more energy than they're creating. Oh, that's a sick burn, huh? That's a fusion powered burn.
That's pretty good dish, buddy.
For the hot fusion community. But what they would say to you is then prove it. And you're saying, I am proving it. Yeah. Here's the test, right?
Yeah. And, we've done almost 10 years of studies and, spent $1 million doing it. And, in the grand scheme of things, $1 million is not that much for these people who are very well funded. Yeah. But for us who are just we are the smallest fusion company in the world right now. And the biggest nuclear fusion company is picking on us right now. I can't talk about the specifics, but they are. And it's really sad to see that all we want to do is collaborate with people and really get this to the world as fast as possible, but we have forces that just don't want it to happen, or they're trying to slow it down or something. And so, again, truth is stranger than fiction. And as we're going through this, this process, Jason, we're learning a lot about ourselves. We're learning a lot about the world. And we're learning about how to teach. And you can't teach everyone the same way.
No.
I mean, you and I are both teachers. We know that it's hard.
In fact, customizing it is where it works the best. You mentioned something maybe in closing here.
Yeah.
As we're wrapping up part 5 of the final.
Yeah. And by the way, this is the last episode for season 1. We're going to be moving into season 2 after this episode. So
cool.
We don't know who's coming on next, but this is the last episode for this season 1 of First Diffusion. So
I've enjoyed being on them. I enjoyed talking about this stuff. And the thing I wanted to ask you is, as we've talked about before, with money, you can do some of the things you want to do next. And what is it that is top of mind for you at the moment?
Yeah.
For if you were to get funding at a higher level, what would you want to do? What are some of the things that would happen next?
Well, in a perfect world, I'd love to start doing clean propulsion technologies where, cars are running on the power of hydrogen, and cars are running on.
When you say propulsion,
yeah, like basically microscopic explosions inside a cylinder engine that make things drive, and the exhaust is clean.
So it's a combustion engine with hydrogen?
Yeah, it would be. Now there are technologies that we could develop if we had enough money where we could actually create, electricity from the arc reactor, like for an electric car. I mean, we could have arc reactors running Tesla cars or running, a BMW i car or whatever. So with enough money, anything's really possible, especially through this technology. And so that's why I feel we're probably getting a lot of pushback from the societal systems, is that it would be if you implemented it too quickly, it could be problematic to the institutions, right? And that's not our goal is not to mess up anyone's stuff, man. Our goal is to just help planet Earth heal. Period.
Well, in that regard, you mentioned on one of the other shows water remediation.
Oh yeah.
So you can take in toxic water or toxic waste of a variety of kinds.
Yes, yes.
And you can untoxify it, so to speak, or detoxify it.
Yeah, because the nuclear fusion event basically transmutates the element into something that is. See, in nuclear fusion, it just always, whatever is like on the outsides of atomic periodic table, it just always tries to make carbon, nitrogen, oxygen, and iron. It's just, that's what it tries to do. Because that's where stability is, like we talked about before. And so whatever's on the outside that's unstable or nasty or whatever, when it goes in the reactor, it just shifts towards this basically planetary core substance.
So you could take what would come from, ironically, a nuclear reactor,
like uranium waste,
and you treat it, and then it becomes non-toxic.
Yeah, it'll either spallate and turn into something else, and then that will spallate and turn into something else gently. You don't have to smash it together.
Right.
Make those fast neutrons and make the baby cry. Don't do any of that.
I do not want to do that.
So, yeah, and using the resonant frequencies of the radio, using the resonant frequency arc reactor, using numbered nodes theory, all of this is possible. And so the future is bright for the world with this technology, and we're really excited to tell you guys about it. And with that being said, Jason, I think we need to wrap up because we're up on, I think, an hour plus today.
I think so.
So again, thank you everyone for tuning in for the First Diffusion episode 7. It's been an honor, and we'll be moving into season 2 in about 2, maybe 3 weeks. We got some things on the pipe here on the business side that are kind of spooling up. So we're going to get
a plot twist. Is there? I told you I watch these shows like I watch like a mini series. I binge watch this stuff.
Let's put it this way: truth is stranger than fiction, and there's some stuff coming down the pipe that is really exciting. And we don't want to talk about it too early, but again, thank you so much for coming along for the journey with Quantum Kinetics. It's an honor to be here with you guys, and keep subscribing. Thank you so much. We just hit 226,000 subscribers in 7 months. We're hoping to hit 1 million in another year here, but that's all because of you guys, and thank you so much. And anyway, thank you, Jason, for coming on the show, and we're going to have you back for sure.
Look forward to it.
But hey, great job, man.
You bet.
Teaching the world nuclear fusion. All right.
It's fine.
So thanks for tuning in. We'll talk to you guys later. Have a great rest of your week.
Bye.
All right, bye.